Okay. So this week is all about solubility, and I go into a whole little introduction here where we talk about this general class of double displacement reactions. I give you guys some examples here, and the real gist of it is we're going to take two things that are soluble, two ionic compounds. We're going to mix them together, and we're going to see the cations and the anions switch, and we're going to result in one or more non-soluble compound that we're going to mark here with an S to show that it's not soluble. And when you wonder what it is that's going to make it soluble or insoluble, it's actually a pretty complicated thing. And what we have here is just a general set of rules. These are just kind of empirical rules that are going to let you predict whether or not something's going to be soluble or insoluble, okay? So if we have any of the group 1 ions, okay, so we're talking our sodiums, our potassiums, you know, everything in that first column of the periodic table. I can pull that up for you guys. So any guy down here, right? Really with I mean, hydrogen will include it, but then we're getting into acid-base chemistry with that. Then we're going to predict that those are going to be soluble. And that also includes anything that has an ammonium ion. So that's the NH4 plus ion. Those are always going to be soluble, and we don't have any exceptions to that, okay? When we're talking acetates and nitrates, we're now talking about polyatomic anions. Those are always going to be soluble. There's not going to be any exceptions to that. When we talk about the halides, so here we're talking about this column as our anions. These are typically going to be soluble, but now we have some exceptions. So the silver chloride or silver bromide, for instance, wouldn't be soluble. Same for mercury, and the same for lead. And the lead is going to be important to us later. We're going to be investigating that a little bit. And then so on and so forth. So we got our sulfates. Those are going to be mostly soluble. And then we get into the ones that are going to be generally insoluble, okay? And the only real exceptions to most of these are going to be that first column and the ammonium cations. When we mix them with these anions, we're going to generally get something that's going to be soluble. So that's generally how we can kind of logic our way through this. So if we come down here to this table, if we're using our rules, we're going to start off in this first column here, or first row here with chloride, and we're going to have this first column with silver. So this would be mixing silver with a chloride, right? So is that going to be a soluble or insoluble one according to our rules? Anybody know? No? Okay. So if we come up here, that would be this rule number 3. So we have our chloride mixed with silver, which is one of our exceptions. So chloride's normally soluble, but it's an exception when you have silver. So that means that silver chloride is going to form a precipitate, okay? And if we come down here, we can write the net ionic equation down here as a silver cation mixing with a chloride anion to form silver chloride solid, okay? So what we want to do is we want to make a note in this table of each one that's going to form a precipitate, and we want to have some little description of what that precipitate looks like. And in order to do that, I provided you guys with an image here that's going to show you all of the different reactions when they're mixed together. So this whole row right here is silver. This whole column is chloride. So our silver chloride is right here. And we can see that that makes like a little white precipitate. So I would come back here, I would write in white precipitate, and then I would come down here and write a net ionic equation for this because it formed a precipitate. And I'm not going to do that for ones that don't form a precipitate because that would just be silly. It would be just silver cation plus chloride anion goes to silver cation plus chloride anion. Nothing happens. There's no reaction, so you don't write a reaction out for it. So that's what you guys are basically going to do. You're going to go through here. You're going to take a look at this picture. And you're going to take a look at what forms a precipitate and what doesn't, right? So this one doesn't, this one doesn't, this one did. This one formed kind of a little bit of a precipitate there. This one's got one. This one's a definite like yellow precipitate. And you're just going to make your notes down there and you're going to write out a net ionic reaction for all the ones that formed a precipitate. Then for the second part is actually pretty easy for you guys because it's really something we talk about when we're in person and kind of work through it together a little bit. But you wind up getting, I gave them 5 different bottles and only one of them had lead and the rest of them were water. And they had to use the different tests that they had, the different anions that they got to decide which one had the lead in it. And they wanted to base their conclusions on the solubility rules. For you guys, it's really going to be a little bit easier than that. If you go back to the data that I gave you, this is what happens when we take lead and we mix it with each one of the different anions. And you can see pretty much all of them, with the exception of nitrate, is going to form some kind of precipitate or at least a cloudy solution, right? And then you come down here and you take a look at the different unknowns that you got and you decide which one of these is the same as the lead based on the results that you got. And it's pretty obvious it's number 3 because that's the one that looks like that picture because it's the same picture pretty much. Because it doesn't translate great to virtual, but that's pretty much it. Is there any questions about any of that? So after you're done doing that, you're going to come down here and you're just going to describe what it is that makes you think whatever unknown you thought it was is going to be lead and how you would know that. And be kind of descriptive, you know, use some of the language from the table up there to make me think that you kind of like thought it through a little bit. And that's pretty much it. That's the whole lab. When we have carbonate here, right, that has a -2- charge, right? And then if we have sodium going with it here, that means we're going to need 2 sodiums for every carbonate. So if this did form a precipitate, that would be Na subscript 2 CO3, right? Because you're going to need 2 of these and you're going to need to indicate that in your equation, right? Mm. Let's see if we can come up with a good example here. So one that should form a precipitate in our example here is going to be when we have zinc aqueous. This is a 2+ cation. You can see that in the table, right? And then when we mix that with hydroxide and we look at our solubility rules, we can see that hydroxide is going to typically form some sort of solid, right? So we have 2, we're going to need to have 2 hydroxides with this negative charge to counterbalance this +2 charge on the zinc. And that's going to form zinc. And I'm going to indicate that there's 2 hydroxides by using this subscript down here, right? I now have to balance this equation by placing a 2 there so that I have mass balance on both sides. So don't get confused about how to balance these, you have to balance the charge in this case in order to write out the right reaction. Does that make sense?
Yes.
Yeah. And we should also, for completeness, put an S here to indicate that a solid was formed.